Question 5 is the electron spectroscopy that we did long ago. As a quick review, we're going to run over how to solve one of these problems. If you'll notice, we have binding energy per electron and then relative number of electrons. The first thing you should do whenever you see one of these problems is see which end the higher energy is on. In this case, 647 is much bigger than 0.0980 times 10 to the 18th times 10 to the 18th gives you the same scale and magnitude, which tells you that this side over here is the higher energy. And this is the lower energy. Which then tells me that these are the inner electrons, because the closer they are to the nucleus, the harder they are to remove. And then these are the outer electrons because they have the least amount of energy to remove, okay? From there, it's just a matter of labeling. Some other key hints to tell you, this is 1 high, this is 3 high, so there are 3 times as many electrons. Not to say that there's 3, but there are 3 times as many electrons here than there are here. So if I were to think about my orbitals, S, P, D, F, S has 2 electrons, P has 6 electrons, D has 10 electrons, F has 14 electrons. The only place where we see a tripling is between S and P as we go from 2 to 6. So this tells me that all the small peaks are S orbitals, all the large peaks are P orbitals. Again, just some hints. Once you have that, you go, okay, well, this then would be your 1s, 2s, counting from left to right and going through your filling process. 2p, 3s, 3p, 4s. Okay, left to right. And because each of these peaks are all the way up to the line, we know that they're full. Why? Because there's exactly triple the amount of electrons here than here, which means we went from 2 to 6. So that tells us that this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay? If we were to have an odd number, so let's say like s1 for the 4s, it would only come halfway up. Alternatively, our scale would need to be changed so it would show 6. This only shows multiples, not numbers of electrons. You need to be able to read between the lines. 1 would look like this, again, or such. But let's just hear that so we don't confuse anyone. But that's how you write the configuration. We just go highest to lowest. 1s, first peak is 1s, second peak is 2s, third peak's 2p, and keep going and make sure your relative numbers match up. In this case, we have 3 times as many, which means we go from 2 to 6. Next question, it says, identify the element. Well, what element has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2? The way you handle that is you go look at a periodic table. We would go look at the 4th row in the S block, second one from the left. So I don't pull out your periodic table, look at it. You're going to go 1, 2, 3, 4 rows down, and the S block is that left double column there with the lithium and beryllium kind of at the top of it. Hydrogen and helium should both be there, but that is a thing we've discussed and argued about before. So your S block is those left 2 columns. Let's go down 4 and then over 2. So you go down 4. So hydrogen, lithium, sodium, potassium is 1, 2, 3, 4. And then over 2, potassium, calcium. Calcium is your element. Now, all they expect on the test is the symbol, not the name. But we know better. We can actually write the name because we are awesome. We memorized that that is calcium. Over here, we can also write the abbreviated structure, which in this particular case would be AR4S2. Either way works. Either of these answers are awesome. B is a bit of a curveball because we haven't explicitly talked about it in class, but let's go ahead and go through it. This is largely something that you were expected to cover in physics, and I was going to recap at some point in the near soon, but we didn't get a chance to get there because, well, the world ended to a small degree. So, if we look at our equation sheet, there's two equations under atomic structure, and this is what this is, atomic structure. The first is E equals H times that little kind of V symbol. And the second is C equals lambda V. Let's talk about these equations. The first is the Planck equation. It tells you the amount of energy required to, or held by an electron, or by any real particle, in this case particularly light. E is the amount of energy held by light, and that is equal to a constant called the Planck's constant, which is on your equation sheet as H, which is 6.626 times 10 to the negative 34th joules per second, times V. This is not an actual V, it's a slightly stylized V. This V stands for frequency. It's actually a Greek letter, they just don't write it particularly well. The second equation we have is the speed of light equation. It says that the speed of light, which is c and constant, is equal to the wavelength times the frequency. Okay, so at this point we have two equations we can walk our way through. The speed of light is a constant. It's given to you. It is 2.998 times 10 to the 8th meters per second. Wavelength is what we're looking for. Frequency is what we need to find. But we can find the frequency given that the energy, which is right here, equals Planck's constant times V. So what I'm going to do is I'm going to solve this symbolically. If you'd prefer not to, that's okay. So the first things first, I need to find the frequency. So E equals H times V. I'm going to do this over here just so I don't run out of space, which rearranges to E over H equals that kind of fancy V. Now, if you are uncertain what to do here, you can plug in your numbers. You can plug in the energy required to remove a valence, which is the outermost electron, which is 0.980 times 10 to the negative 18th, divide by Planck's constant, which is 6.626 times 10 to the negative 34th joules per second, and they'll give you a frequency. You can then take that frequency and then go ahead and plug it into this equation here. I'm going to just be lazy and cheat, and instead I'm going to plug it in directly. So I'm going to get C equals lambda, which is wavelength, times, just plugging this in instead of frequency, I'm going to say E over H. If I rearrange this, I get lambda equals C times H over E. Okay, all I did was just plug it in and solve it symbolically. Again, if this is uncomfortable to you, use the actual numbers. Whatever number you get here goes here. C is 2.988. If I go ahead and plug this in, I get lambda equals 2.998 times 10 to the 8th times 6.626 times 10 to the negative 34th. All divide by 0.980 times 10 to the negative 18th. If ever there's a problem where you need your parentheses, this is it. Please make sure you use your parentheses appropriately. Divide by this entire quantity. If you do all your math very, very carefully, you should get your wavelength equals 2.08 times 10 to the negative 7th meters. And there we go. Okay. So let's just recap this really quick. Whenever you have a electrons or light or energy, you're talking about atomic structure, it's probably going to be these two equations. Remember, most of these are constants given to you. You can get the energy from here. Wavelength is lambda. The little funky v is frequency, or how fast that's vibrating. We'll probably do a crash course on light and waves at some point in the near soon, but for right now, that's your answer.